Hello again, this is the data engineering course, and this is the second part of the video about the data integration. And in this section, I'm going to discuss about the instance-based or data integration. So what is instance-based or data integration? When we are dealing with the data integration, we need to describe. Okay? We should describe the procedures to establish whether the two instances are not duplicated. Okay? Because when we are dealing with the schema, okay, the first was about the schema. The schema, it doesn't matter if schema are duplicated or it is similar, because we want to integrate the schema. But the data, the issue when you want to integrate the data, if the two instances are duplicated, then it will cause the data analysis more not reliable. Okay, so there are some relevant approaches for this integration. You can use the probabilistic approaches. So let's say the Bayesian inference problem. You want to see whether the data already exists or not, and you want to see the probability. Okay? And we can also use bias decision rule or some other like the clustering algorithm, like the expectation and maximization. The other relevant approach, we can use the supervised and semi-supervised approaches, or we can use distance-based techniques or the unsupervised techniques. Okay? So the clustering, bootstrapping, or the hierarchical graph model. So those kind of things are techniques related to the instance-based integration. And I think we cannot discuss all those techniques. I'm just showing some possible explain techniques, like what we are going to learn in this course. Now, the instance-based data integration is more related about how to detect the tuple duplication and inconsistency. So there are many techniques, and I'm going to just explain about how, if we want to check the nominal attributes. The nominal attributes mean any text or any string. We can use the edit distance. We already learned about the edit distance. Affine cap distance. We will check a little bit more about the affine. The Charo. Okay, there's another algorithm we call Charo. N-grams. We already learned about the n-grams. And other techniques, of course, I cannot explain all. If you want to check the numerical data, we can check based on the distribution, or there are some extended version of cosine similarity. For example, the WHIRL for the numerical data. Or we can use the outlier or noise detection. Okay. For the edit distance, actually, the example that I show you is a very simple edit operation. In fact, there are many algorithms available for the edit distance, and they call it the algorithm is based on the longest common subsequences. So some algorithm for this one is the string edit distance. This is the popular, or maybe this is the most common algorithm used for measuring the edit distance. We call it Lippenstein's. Or there are some other techniques like Needleman-Wunsch and Wagner-Fisher algorithm, Hirschberg algorithm, but I will not explain all. The affine cap distance is one of the algorithm for measuring the distance. If you already learned the string edit distance, the addition, deletion, you want to check how many characters are deleted, how many characters are added. So that's the common of the Levenshtein. But I would like to also explain another approach. We call it the affine cap distance. In the real life, this is a very common situation data that have caps longer than one character. And affine cap, the algorithm distinguish this one. it will calculate the cost of opening cap of any length. It is applied to the first character of cap like A, and cost of continuing the cap when there is more than one empty space in a row, and it is applied to the remaining characters of a cap, like this one. I want to compare between the Alexander Johansson and the Alex GSO. Okay, if you are dealing with the Levenstein, then you will just consider about the addition, okay, and the deletion. So how many letters are deleted from this one, and then how many letters are added from this one, and then you can measure based on the similarity that we already saw before. In this affine cap algorithm, it will consider the result based on this alignment. Okay. So this alignment means if I have this Alexander Johansson like this one, and then if I want to align it, then I will put the empty space. This empty space means, yeah, I have the mismatch 1, 2, 3, 4, 5 like this one, and I have the Johansson because I have J and then S and then O, then I will also have the empty space here. So this one is better than this one, because yeah, the first S is in the first letter S, and this S is in the second letter of S. No, if the space, the number of space, you can see this is 1, 2, 3, 4, 5, okay, and this space 1, 2, 3, 4. So if we are applying with the longest common subsequence, okay, so if we have the longer one, the distance will be longer. Okay, so if we can shorten the distance, okay, yeah, we can say that this one is shorter, but yeah, the cost for this one is much better. So that's why in the affine cap algorithm, they will consider this alignment is better than this one. So the affine cap algorithm is something like this one. Okay. We have the global alignment. Okay. And we have the ix and iy. I can say something like, yeah, we want to find whether there's the gap between this one and this one. Okay, so I can have this one. The gap open score is -3. Okay, and the gap extension score is -1. Okay, how can I achieve this one? You can see this one, the Alex, okay, Alex to Alexander. What does it mean? We have one gap opening penalty, okay, one gap opening penalty, and 4 multiplied by gap continuing penalty. So here we have the, yeah, this is already defined. Okay, so the open score is -3 and extension score is -1. So this is already defined. Predefined score. Okay, and then I would like to check how many, okay, how many of the penalty that I will consider. So here, the opening penalty, okay, the opening penalty here is already 1, okay, and then, yeah, I already have, if it is already the first, the opening is already different, then I will give the penalty higher. and the next or the extension will be just -1. So you have -1, -1, -1, and -1. Okay, so for the Alex to Alexander, so we have this one -3. Once it is different, then it will give a high penalty cost, and the remaining will be just -1, -1, -1, and -1. Then we have -7 for those. Okay. And we have the Johansson. Okay, so what happened to Johansson? So Johansson, okay. So J, and then okay, this is the first, then it is -3. Okay, and then what happened next? Yeah, if you have this 1, 2, 3, okay, so it means -1, -1, and -1. Okay, so if you have Johan is less value than this one. Okay. In this case, we have the yeah, we have my -3, -1, -1, -1, and then we have -1. Okay, but what about this one? Yeah, we have -3, -1, -1, -1, and then we have the first one, we have -3, and then we have maths, and then we have -3. Okay, so this will show higher, but this one, after we have -3, -1, -1, -1, -1, so we have maths, and then we have another -3. So the cost of the or the total penalty gap, okay, if we have this one, okay, so we have -7 because of the first one, and then -6. -6 is from the Johan. Okay, so -3, -1, -1, -1, and then we have only the -3. Okay, so we have the -3. Sorry, SO, because we have okay, because we have the SO and we are dealing with the SON. Oh, wait a moment. Oh, I guess this one, something wrong in the Johansson. So yeah, we have the S. Yeah, I guess is this. We have one more here, but I don't calculate. I don't calculate it here. Okay, so it's not 3, but it should be 4. Okay, yeah, it should be 4. Is it 5? Yeah, it should be -7. Okay, it should be -7, and then yeah, we have the this one -7. So -7 plus -7, it means -14, and -14 -3. Okay, so we have the -17. Okay, yeah, I'm sorry. So this one should be -17. Then we have a -17 for this one. But what about if this one? So we have -7 for this one, and then -3, -1, -1, -1. So we have -6, and then we have this one -3, and then we have -3. So we have -6, then -12, -12 plus -7. So it means -19. Okay, then now of course this one is better than this one. Okay, there's another algorithm, we call it Jaru. Okay, Jaru-Winkler distance. It is also to measure the distance between two strings. Okay. Okay, maybe let's see the example. Okay. We have like Tris and Crit. Yeah, this is a very unique example here. So we are going to calculate the number of matching M. M is the number of matching character, and then T is half the number of transposition. We want to calculate the S1 and S2. So two characters from S1 and S2 are considered matching only if they are the same and not farther than this one. So this value means the rounded value into the lower value, and we want to find the maximum length of S1 and the maximum length of S2 divided by 2 and then minus 1. So if you take a look on this one, we have the floor. Okay, so we have, what is the S1? It is 5. Okay, the length. Okay, the length of S2 is 5. So what is the maximum S1 comma S2? Yeah, the maximum of 5 comma 5, then it means 5. Okay, and then 5 divided by 2 minus 1. Okay, so we want to floor. Floor means, okay, you can see here, yeah, we want to floor. Floor means, yeah, where is it? Yeah, we want to floor this one, then it means 5 divided by 2. 5 divided by 2 is 2.5. So we want to go round to the lower value of integer. So 2 minus 1, it means 1. Okay, so this is the threshold value. Okay, and then after we have this threshold, so we want to measure the Jarrow-Winkel distance. Use a prefix scale p, which give more favorable ratings to string that's matched from the beginning for a set prefix length. So if we have the dw, okay, the dj plus l is the length, multiplied by p multiplied by 1 minus dj. Okay, so what is the dj? The dj is the Jarrow distance for string s1 and s2. Okay, and l is the length of common prefix at the start to the string up to the maximum 4 characters. And then p is the constant scaling factor. Okay, so p is determined value. Usually in the Winkler's work, it is 0.1. Okay. So there's a kind of standard like p should not exceed 0.25. You can define your p. Okay. So for this one, we have the TRACE, okay, and then CRATE. So how many matches so we have here? So we have the T and C, so it does not match because the sequence. Okay, we need to match the sequence. Okay. So the matching character, actually it should be in the sequence. Okay. And then R. Okay. R, okay, this is an R, okay, but because the first is different, then we don't care about that one. The second R, so it's the same, and then A and A is the same, and then C and T, okay, they are different. Okay, and the last one is E and E, so they are the same. So the matching character is M equals to 3. Okay, although C and T appear in both strings, so they are farther than 1. Okay, so if we have this formula, okay, then because they are farther than 1, we can put this T, okay, because they are not, the T and C is different in the length, so we just put T equals to 0. Okay, so what is M here? M equals to 3, then we can calculate 1 divided by 3, and then multiply by 3, 5 plus 3 divided by plus, and then 3 minus 0, because we don't have any T, t is half the number of transposition, okay, because this one is less than 1, okay, so we have just used the 0 to indicate this one, and then yeah, we can calculate this dj, okay. So the dj, if m equals to 0, then it is 0. If not, then we will take this one. So you can see this one, I guess. Oh, okay. Sorry, I have another example. Yeah, maybe I will just use this one. Yeah, maybe this one is much better for giving you the explanation about the charo. If you have Martha, this one, and the Martha with HT, so it's the only different this one. The length is 6, okay. S1 is 6 and S2 is 6, and we have the M is actually yeah, because this distance is T and H is the distance is short, so we can say that yeah, they are still matching. Okay, so for example, this one in the T and C, so C and T, so they are already away in some distance, so we cannot say that they are in the same match. So maybe yeah, if you take a look on the Google, okay, so if you have the different like this HT and TH, yeah, they are still considered the same, and Google can revise according to this maybe mistype. Yeah. So there are mismatched character T and H and HT, and it leads to T. T is 2 divided by 2, and yeah, we call it the T equals to 1. Yeah. And then yeah, we can calculate the DJ. So the DJ is this number, okay, M. Yeah, we can just put the M, and then M is M, and then this is the T. Then we can get the value DJ is 0.944. And to find the Jaro-Winkler score using the standard weight P equals to 0.1. So we will continue with the L equals to 3. Okay. So what is L? Okay. So if we take a look on this one, L is the length of common prefix at the start of the string, common up to maximum 4 characters. So here we have MAR. So the first 3, they are matching. So we call L equals to 3 for this matter. So the DW or the Jaro-Winkler is the 0.944, which is from the DJ, plus 3 is the length, and the P is 0.1, and multiply with the 1 minus 0.944. So we can get the Jaro-Winkler distance is 0.961. So they are very similar. Okay, even though they have only mistyped this one, then we can say this is very similar. So if it is very similar, then maybe you can search on the database what is the correct word for this one. The n-grams, you already learned the n-grams. We can have the n is a number, an integer number, and let's say if it is Cohen, yeah, you can have like COHEN, COOHHEEN, COSOHEHEN. Okay, so this is to represent the n at less than k. Okay, so if I have like n equals to 3, okay, then yeah, anything that is below than k, is the number of the characters. Okay. If we have n4 or 5 is competitive on the rival test, it does not seem to be competitive with small values of n on matching tests, but it is useful as a fast approximate matching scheme. So usually the n-grams, you have like 1 gram or 2 grams or 3 grams. So if it is more than 3, it will be time consuming and it's not that useful. Cosine similarity. So in the cosine similarity, we want to calculate the two factor. Okay? Let's say A and B. Okay? We have the length of A, and then we have the length of B, and then we want to calculate it. So let's say I have this string, I have this number, and I have this number. So this number can be calculated. So 3 multiplied by 1, and then 2 multiplied by 0, 0 multiplied by 0, 5 multiplied by 0, okay, 0 multiplied by 0, and so on. And then we will get the product A multiplied by B is 5. And then the length of A, yeah, you can just use the like Euclidean distance. Okay, so the Euclidean distance means the A square, and then you do the summation for all the values, and then do the square root. So let's say this is the value, and this is the value for B, and yeah, the cosine similarity between A and B is 0.3150. So it means the similarity between them are not that high. Yeah, you can use the idea of cosine similarity like this one. Okay? If we have the A, B, C, D, E, okay, and all of them are in the we have this like the database one, okay, and then this is the database two, okay? And then you want to combine. You have A, B, C, D, E, and you want to combine F, G, H, I. Oh, this is J actually. Sorry. Okay. And then you have the data. Okay, the data is very high, and the maintenance is medium, and the door is 2, and the person is 4. Okay. So you want to check the similarity. Okay. So the similarity between A and B. Okay. So actually this one is the same, and this one is the same, and this one is the same, and this one is the same. So the cosine similarity is 1. Okay. What about A and C? This is 1 and 1. Okay, and then this is 1 and 1. This is 1 and 1, and maybe this is 1 and 0. Okay, so yeah, you can have the 0.75 and so on. So for example, the A and J. Okay, A and J, this is very high, this is very high. Okay, this is medium, and this is small. This is 2, and this is 3, and this is 4, and this is more. Then it's different. So there's only 1 among 4 that match. Okay. So we can use this cosine similarity as well to measure. So the last one that I want to explain to you is when you deal with this data integration, there might be some redundancy and inconsistency. Okay? And this is a very common issue when you are dealing with the data integration. And handling the nominal data will be different with numerical data. So usually we will use the correlation analysis. Yeah, and the correlation analysis can be distinguished into two, whether the correlation analysis for nominal data or the correlation analysis for the numerical data. Yeah. So the correlation yeah, is kind of transformation to see the similarity. The correlation in nominal data is more likely about the observation. Yeah. When we deal with the redundancy, yeah, we want to check whether the data occurs in multiple database are redundant or not, and if the same attribute or object may have different names in the different database, yeah, it's also affect the data integration. Okay? And one attribute may be a derived attribute to another table. Yeah, maybe the age and date of birth. Okay, so this kind of redundancy may appear. So the redundant attributes may be detected by correlation analysis and covariance analysis. So the careful integration of the data from multiple sources may help to reduce or avoid redundancy and inconsistency and improve mining speed and quality. In this chapter, I guess, yeah, we will learn the very basic correlation analysis with the chi-square. If you know the statistics, yeah, so the chi-square analysis is the most common way to measure the correlation analysis of nominal data. So the idea is we want to see the observed data and minus by the expected value, and we will do the square and divide it by the expected for the summation. Yeah. The expected value is likely about the whether the count, if the count of A multiplied by the count of B divided by the total data. So the chi-square statistics tests the hypothesis that A or B are independent. So there is no correlation between them. And the test is based on the significant level R minus 1 and C minus 1 degree of freedom. R means the row and C is the column. If the hypothesis can be rejected, then we can say that A and B are statistically correlated. So the hypothesis is related with the p-value. Okay. The larger x chi-square, the more likely the variables are related. Okay. So we can just see the chi-square. If the value is high, then yeah, it's more likely highly correlated. But note that the correlation does not imply causality. Okay? So for example, yeah, if the hospital number of hospital is high and the number of car theft in the city also high, and based on the observation, they are correlated. But actually, the causality is based on the third variable, which is the population. Okay? Because of the higher population, of course, the number of hospital will be higher, and because of the higher population, then the car theft also high. So there's a causality, but yeah, we cannot see this immediately with this kind of correlation. So let's say, yeah, this is an example. I have a fiction and male and non-fiction and female. So based on the observation, there are 250 male who like fiction, okay? But the expectation is 90. Okay? So this is the observation, and this is the expected value. Okay? And if you want to measure the chi-square, then yeah, you can just fit into the formula 250 minus 90 divided by 90, and then we have the 50 minus 250, 210 divided by 210, and so on. So we will get the value of chi-square is as much as 107. In this case, the value is quite high. Then we can say that there is a high correlation between the gender and the fiction or non-fiction. Okay. So from this 2 multiplied by 2 table, the degree of freedom is 2 minus 1, 2 minus 1, which is 1. Okay. And the chi-square value needed to reject the hypothesis at 0.001 significant levels. And the significant level is the 10.828 is using the chi-square distribution table. Since the confidence value is above this, then we can reject the hypothesis that gender and preferred reading are independent. Okay? So we cannot say that they are independent. They have a high correlation. So based on the high chi-square value. So we can calculate that the two attributes are strongly correlated for the given group of people. Okay. If we are dealing with the correlation analysis for numerical data, we can use the person product moment coefficient. Okay. This is the formula. I think I will not discuss the formula in detail, but basically we have the A and B, and the A and B are two different columns, and you want to see whether the numerical data between the two are correlated or not. So we can also deal with the standard deviation of A and the B, okay, and we will do with the cross products of A and B. And the result of R is a value, and if it is higher than 0, then A and B are positively correlated. The higher value, the stronger the correlation. If it is 0, then they are independent. If it is less than 0, then it is negatively correlated. Yeah, you can see with the visualization, if it is like this one, then it is a negative correlation. If it is nearby 1, then it is a positive correlation. If it is 0, then the data are independent. There is no correlation. Okay, and yeah, there is another aspect to measure again for the numerical data. We can use covariance. Yeah. The covariance means we want to see the variance between two columns A and B, and then we want to check the co. Co means the co is if the two data are in the same aspect. So we want to see like this one. We have the A expected value of A with regard to the mean, and then the expected value of the B with regard to the mean. It means for every of this value will be check the different with the mean. But we have in the covariance, okay, we don't consider the product of A and B, but in the person moment variation we have the A cross product of AB. Okay, so we want to see the consideration between A and B. If it is highly correlated, then we can see this one from the correlation, but in the covariance we don't consider any cross product between A and B. Okay. We still see this correlation coefficient, but it is more about the covariance. We call it this is covariance, not correlation. And the idea is still the same. The positive covariance, if it is higher than 0, then A is larger than its expected value, and B is also likely to be larger than its expected value. Okay, so the interpretation is a little bit different. If it is negative covariance, then yeah, the covariance A is less than 0, then the A is larger than its expected value, and B is likely to be smaller than its expected value. Okay. If it is 0, yeah, then it is independent. Yeah. So when it is independent, the some pair of random variables may have a covariance of 0, but are not independent. Only under some additional assumption, like the data follow multivariate normal distribution, does a covariance of 0 imply independence. So you need to check if it is if the covariance is equal to 0, then whether it follows the multivariate normal distribution or not. If it follows the multivariate normal distribution, then yeah, you can say that the covariance between the two data is independent. There's an example about the covariant example. Let's say I have two stocks. Okay? So there's two stocks A and B. Okay? This is the stock A and then this stock B. Stock A, stock B, stock A, B, A and B, and A and B. So if the stocks are affected by the same industry trend, will their price rise or fall together? Okay. So I want to know whether they are increasing or decreasing at almost the same. So the expected value of A is 2 plus 3, 5, 4, 6, and 2, 3, 5, 4, 6. And then B is 5, 8, 10, 11, 14. Okay. So the expected value is the same with the average. And then you want to measure the covariance. Okay, this is the covariance value, and yeah, you will get the value is 4. So the A and B rise together since the covariance of A and B are greater than 0. Yep, you can also measure the correlation based on the covariance. Okay, so when you understand the covariance, then you can just do the division with the standard deviation of x multiplied by standard deviation of y, and yeah, you can get the correlation. So basically, this idea of the correlation, yeah, is similar with the Pearson correlation, but we use the covariance to indicate the correlation. What is the drawback of correlation? So when we have the correlation, we can see some patterns. Okay, if we can see some patterns, and if it is a function, okay, then yeah, we cannot see whether it is a correlation or not. So for example, x and y, I want to see the correlation between the two. Okay, so we have -3, -2, -1, 0, 1, 2, 3, and then we have 9, 4, 1, 0, 1, 4, 9. Okay. And what happened to this one? If you take a look on this one, the idea is yi is the result of xi power of 2. Okay. So there is a dependency, so it is not independent. Okay. And if we want to measure the mean of x is 0 and the mean of y is 4. Okay. And then this is the standard deviation of x, and this is the standard deviation of y. And if you want to measure the correlation, then you will get this value, and yeah, the correlation is 0. There is no correlation between the two. Okay. Oh, what does it mean? Yeah, because we know that this is a function. Okay, there is a function of this one, and yeah, when you want to see the correlation, it seems there is no correlation, but we have the high correlation, or we can say this is the dependence. Okay, it's very dependent. Then it should be very high on the correlation value, but it's 0. Okay, so when the dependency has a function like this one, then yeah, it still has, this is the drawback of the correlation. Okay, then I guess that's all about the data integration. So you already learned about the data integration issues, and yeah, you learn many approaches for the schema base, and you learn also many approaches for the database or the instance base. And at the end, you learn about how to handle the redundancy and inconsistency using the correlation in the nominal data and the numerical data. Yeah, I guess that's all about the video for this section, and hope to meet you in the class for the further discussion. Thank you.